Hi everyone. So today we have a research paper. It is a quite famous research paper because the authors are leading names in the AI space. Geoffrey Hinton, Ilya, and Alex Krizhevsky. And this is a image classification which they did. I think this was published in 2013 or 12. This paper. So we'll just read it. I have tried to read it once. Let's read it and see what we can understand. So they trained a deep convolutional neural network to classify 1.2 million high resolution images in the ImageNet LSVRC 2010 contest, and it has 1,000 different classes. So it is around 2010. So this work was done in 2010, but I think they published 2013. On test data, they achieved top one and top five error rates, and they won the competition. Top one and top five error rates of 37.5%, 17%, considerably better than the previous state of the art. The neural network has 60 million parameters, and 650,000 neurons, consisting of five convolutional layers, some of which are followed by max pooling layers, fully connected layers with a final 1,000-way soft max. Okay, even if we do not understand most of the things, let us read the abstract, then we will read the introduction, and then we will see. We'll skip the part which we do not understand and maybe try to learn more about it later. To make the training faster, we use non-saturating neurons and a very efficient GPU implementation convolution operation. This very efficient GPU implementation here means that they use two GPUs, and because one was not the memory limitations were there, so they implemented two GPUs, and it was a very, I think, fully efficient implementation. To reduce overfitting in the fully connected layers, we employed a recently developed regularization method called dropout. So you see a regularization method. We were studying in our machine learning classes, and there are various regularization methods, and here they introduce a new one called dropout. We also entered a variant of this model in the 2012 competition and achieved a winning top 5%. Okay, so they entered in the competition in 2012, a variant of this model, and they won the competition. Current approaches to object recognition makes essential use of machine learning method. To improve their performance, we can collect large data set, learn more powerful models, and use better techniques for preventing overfitting. Overfitting, as we know, is when the model learns the test data too accurately, so it is not able to predict or classify based on the unseen data. They highlight that the okay, they have a large data set, new large data set, including label me, which is consist of hundreds of thousands of fully segmented images, and ImageNet, which consists of over 15 million labeled high resolution images in over 22,000. To learn about thousands of objects from millions of images, we need a model with a large learning capacity. However, the immense complexity of the object recognition task task means that this problem cannot be specified even by a dataset as large as ImageNet. So our model should also have lots of prior knowledge to compensate for all the data we do not have. So they're saying that since they do not have a large data set and my model cannot be trained on that data set, so their model should have a prior knowledge for all the data that they do not have. CNN constitutes of one to such class of models. Their capacity can also be controlled by varying their depth and breadth. They can also make strong and mostly correct assumptions about the nature of images. Compared to the standard feed-forward neural network, similarly sized layers. CNNs have much fewer connections and parameters, so they are easier to train, while their theoretically best performance is likely to be only slightly worse. Okay, here is the key point I think. What is the specific conclusion of this research paper? So the specific contribution of research paper are as follows. We trained one of the largest CNN to date on the subset of ImageNet. ImageNet has a 15 million, but they trained on a 1.5 million dataset and achieved by far the best result ever reported on this dataset. We wrote a highly optimized GPU implementation of 2D convolution and all other operations inherent in training CNN, which we make available publicly. Our network contains a number of new and unusual features, which improves its performance and reduces its training time, which are detailed in section 3. The size of our network made overfitting a significant problem, even with a 1.2 million level training example. We use several effective techniques for preventing overfitting, which are described in section 4. Our final network contains 5 convolutional and 3 fully connected layers. That seems to be important. We found that removing any convolutional layer, each of which contains no more than 1% of the model parameter, resulted in inferior performance. Our network takes between 5 and 6 days to train on two GTX 583 GB. Okay. All our experiments suggest that our result can be improved simply by waiting for faster GPUs and bigger dataset become available. So this is the part of dataset. They have a 15 million high resolution dataset, but they trained on the 1.5 million. ImageNet consists of variable resolution images, while our system requires a constant input dimensionality. Given a rectangular image, we first rescale the image such that the shorter side was of length 256 and then cropped out the central 256 patch from the resulting image. Architecture ReLU nonlinearity. So I think this is an activation function which has become standard in the for the hidden layers. But I think this was first used here. They used ReLU. Rectified linear units. We are not the first to consider alternatives to traditional neuron models using a four-layer CNN network with ReLU solid line. This is the ReLU. This is the epoch. This is the training error rate. Okay, training on multiple GPUs. GTX has only 3 GB memory, which limits the maximum size of the network that can be trained on it. It turns out that 1.2 million training examples are enough to train networks to be 1 GPU. They spread the net across 2 GPUs. Local response normalization. overlapping pooling, overall architecture. As depicted in figure 2, the net contains 8 layers with weights. The first 5 are convolutional and the remaining 3 are fully connected. The output of the last fully connected layer is set to a 1000 way softmax, which produces a distribution over 1000 class levels. Our network maximizes the multinomial logistic regression objective, which is equivalent to maximizing the average across training cases of the log probability of the correct level under the prediction distribution. Not understand anything. They have also provided the code. We cannot describe this network in detail due to a space constraint, but it is specified precisely by the code and parameter files provided here. This is the illustration of their architecture. Strain of link. How did they reduce the overfitting? First thing they did was data augmentation. The easiest and most common method to reduce overfitting on image data to artificially enlarge the dataset using label preserving transformation. We employ two distinct forms of data augmentation, which allow transformed images to be produced from the original images with very little computation. So the transformed images do not need to be stored on disk. In our implementation, the transformed image generated in Python code on the CPU, while the GPU is training on the previous batch of images. So these data augmentation schemes are in effect computationally free. Okay. The first form of data augmentation consists of generating image translation and horizontal reflection. We do this by extracting random 224 into 224 patches and their horizontal reflections from the 256 cross 250 images and training our network on these extracted patches. This is the reason why the input images in figure 2 are 224 into 224 dimensional. Okay, 224, 224, 3 dimensional. And second form of data augmentation consists of altering the intensity of RGB channels, red, green, blue channels in the training images. Okay, we perform the PCA on the set of RGB pixel values throughout the ImageNet training set. Second thing for reducing overfitting is dropout. Okay, the recently introduced technique is dropout. It consists of setting to zero the output of each hidden neuron with a probability of 0.5. The neurons which are dropped out in this way do not contribute to the forward pass and do not participate in the back propagation. So every time an input is presented, the neural network samples a different architecture. But all these architectures share weight. This technique reduces complex co-adaptation of neurons, since a neuron cannot rely on the presence of particular other neurons. It is therefore forced to learn more robust features that are useful in conjunction with many different random subsets of other neurons. Details of learning. We trained our models using stochastic gradient descent with a batch size of 128 examples. This we saw in our machine learning introduction exercises. This is the gradient descent, and it is a batch size of 128 example momentum of 0.9 weight. The weight decay momentum we have not read, but the result top 1 and top 5. Figure 3 shows the convolutional kernels learned by the network's two data connector layers. The network has learned a variety of frequency and orientations. Our results show that a large deep convolutional neural network is capable of achieving record-breaking results on a highly challenging dataset using purely supervised learning. So we know what is supervised learning, where we provide a level. It is notable that our network performance degrades if a single convolutional layer is removed. For example, removing any of the middle layers results in a loss of about 2% for the top one performance of the network. Okay. To simplify our experiments, we did not use any unsupervised pre-training, even though we expect help, especially if we obtain enough computational power to significantly increase the size of the network without obtaining corresponding increase in the amount of level data. Okay, that's all. We did not understand very much, but let's say we'll read it again. And another article that I was reading was how we did get from artificial neural network ANN to transformers. So it describes what are ANN feed-forward network where each uh, information is passed through different. Then there is a current RNN. Then the what is the drawback of RNN? And then we move into encoder decoder model. So I'm reading it, and once we read it, then maybe I can say that's all. Next video, maybe I can attempt or read it again, understand more, or attempt any particular product.